This video is on thermochemistry, and much of what we do when it comes to thermochemistry is to understand whether a reaction will occur spontaneously. So we're asking, will this reaction occur spontaneously? And how we determine that is it's an interplay of three ideas. Enthalpy, change in enthalpy. There's also change in entropy, and there's also a change in Gibbs free energy of a reaction. Now, these are all the equations you would be using for calculating delta H, which is the change in enthalpy of a reaction. Depending on what you're given, whether it be bond energy, heat of formation values, or a series of elementary reactions, or calorimetry, where you're given the heat or the temperature change where heat is transferred to, say, water per mole of a substance when it combusts. So the variations of all these equations, including here delta S as well as delta G, helps us to answer the question of whether this reaction will be spontaneous through delta G. If delta G is negative, it tells us that the reaction is spontaneous. If it's positive, the reaction is non-spontaneous in that direction. So let's go ahead and work through a problem. Now, these problems can be pretty intricate. You never know exactly. You have to kind of work out depending on what you're given. So if you look at this, you're given two tables. One table is the standard free energies of formation of different substances at 298 Kelvin. The second one is average bond energy bond dissociation energies at 298 Kelvin. That's called bond energy as well. So you're given different bonds. And this here is used to calculate your delta H, your change in enthalpy. This here allows you to calculate the delta G, which is the change in Gibbs free energy of a reaction. So that kind of gives you an idea of how to go about calculating it depending on what you're given. So let's look at what you're asked. Here's the reaction that you see right here. And you want to find the delta H, change in enthalpy for the reaction at this temperature, 298. And so Gibbs free energy formation values will only give you the change in Gibbs free energy of a reaction. This here will give you the change in enthalpy of a reaction. So we're using bond energy, and to do bond energy is to make sure you draw all the different bonds in this reaction. So I'm going to lay out the different bonds given they're all here as well. So I'll draw them all out. And you want to make sure you look at the coefficients, so the stoichiometry, to know how many how much energy to break up all the bonds in the reactants and the products. So let's draw each of these structures. So if you carefully draw, you'll notice 2 carbons and 2 chlorines. So I'm going to put the 2 chlorines on both ends of this structure. And I know that carbon usually makes 4 bonds, so I can see where the 4 hydrogens will lay. So this is the structure. And there are lone pairs around the chlorine as well, but we're not too interested in those. We're really looking at the breaking of these bonds that you see in this structure. So the next structure is now 2 carbons as well. It's a little tight, but we'll find a way to fit them all. Hydrogens, 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 and 1 chlorine only, and 5 hydrogens. The next structure is HCl, and so we draw the Lewis structure out, and we end up with this structure right here. And then chlorine's pretty easy to draw. It's just 2 Cl single bond, and you'll see lone pairs around the chlorine. So we have all our structures. And so to calculate the delta H for the reaction using bond energies, which are these values, you just take the bond energy of the products, which are these 2 substances. So I'm just going to go on identifying who the products are and who the reactants are. So here we have, this is your products, I'm going to circle it, and this is your reactants. And here you have HCl as a product, so here's my product, and here's my reactants. So I'm just organizing how I would be breaking and making bonds as I break reactants, or the bonds in the reactants, and then I make bonds in the products. So I then line up my equation. Delta H of a reaction is taking the negative of the sum of the bond energy of the products, which right here, if we look at all the bonds in the products, we have a CC bond. So CC bond is 347. So I'm just looking at this bond. So there's also a 2Cl bonds. So I'm going to add and sum 2Cl bonds, which is 377. And I'm timesing that by 2 because there's 2 of them. And then there's a lot of CH bonds. There's 4 of them. So 4 CH bonds, which is 414 each times 4. And I think we are missing a Cl bond. So we've got our CH, 4 of them, our 377 our CCl bond, and then our CC bond. Oh, we forgot our HCl bond. So our HCl bond in our product is 431. So these are all the sum of the energy of the bond, or the bond energy of the products. Now we go into the sum of the bond energy of the reactants. So here we're getting into the reactants, and we are going to subtract these two values. So that's why I'm going to put a subtraction sign. So here we have reactants, and the following bonds are in our reactants. I see a CC bond once again, so 347. So here's my CC bond. And now I have 5 CH bonds. So I'm going to take 414, and then I'm going to times that by 5, because there's 1, 2, 3, 4, 5. And then there's also a CCl bond. So CCl bond is 377. Now, if you look at it, we also have our another reactant, which is the CC, or ClCl bond. So that's 243. So you sum up the reactants, you sum up the products, and you subtract each other, and then you take the negative of that. So I'm going to do this part first and then take the negative of that. And when I add up these numbers right here, the top numbers, I get 3,188. And when I add up this bottom numbers, the reactants, so this is products minus reactants, I get 3,037. So 3,037. And when I subtract these two, I get 151, and I always have to take the negative of that. So the negative of that is this value right here, and that's in kilojoules per mole, just as the unit suggests here. So that's to calculate your delta H of a reaction. So we've got that checked off. Now you want the delta S of the reaction. So the thinking behind this is to find the delta S is if we have the S formation, which we don't, we can then calculate that directly from that, but we don't. So we're going to use the delta H and the delta G, so only the delta G of the reaction. So it's just delta G is found by taking, and I'm going to calculate delta G of the reaction over here. So the sum of the products, so the products are, I'm going to write this in over here as well. So here's my products, P, reactants, products, and here's my reactants as well. Again, ways to organize your thoughts. So here I have my products, and so I'm going to sum my products. Negative 80.3 plus negative 95.3. So now I'm going to sum my reactants. My reactants are negative 60.5 plus zero. So here's your 0. So then you're going to subtract the 2. So I'm going to put a subtraction sign right there. And then in adding each of those parts, in adding this part right here, I get 115.6 negative. In adding this part right here, 175.6. Let me double check my calculation on that. That's correct. So subtracting that from this value right here, which technically means you're adding it, you end up with delta G of the reaction being a value of negative 115.1 kilojoules per mole. So if I have delta G, I have delta H of reaction. I can link those two through this equation right here. So I'm going to link it through delta G equals delta H minus T times delta S. So we're going to link them all together. Negative 115.1 is your delta G. Your delta H is negative 151 minus your temperature. Your temperature is 298. And then your delta S is what you're solving for. So solving for delta S, I get delta S to be equal to 0.120 kilojoules per mole times Kelvin. Okay. So if you think about it, it's quite long. There's a lot of steps, but depending on what you're given, you kind of maneuver through what you're trying to calculate in the end. Okay. So now we go to example 2. I just wanted to show you a variety of different ways to solve these problems and the different ways these problems could be asked. So here we have a combustion reaction forming CO2 and water, and it looks like this water is a liquid form. So now we have, it says 2 grams of this hydrocarbon or this alcohol is completely burned according to the equation above. This much heat is a release. And again, I like kind of writing down what I'm given here. So grams is really moles in the end. And it says use the information below to answer the following questions. So now I look at this problem and I have the heat of formation and I have my entropy of formation values as well. And notice the units. This is in kilojoules and this is in joules. So make sure you always note the entropy unit. Oftentimes it's in joules rather than kilojoules. So here I have all my values for my reactants and my products from the reaction. So the first question is, it's asking for the molar heat of combustion. So the molar heat of combustion means I'm looking at this equation where I'm finding delta H equals Q over N. How do I know to use this equation? Because it's heat of combustion. So I'm going to find delta H. But I can actually use heat of formation in order to find the heat of combustion, but it's easier to find it using this equation because you've got your Q and you've got your N, which you just need to convert from grams to moles. So let's do that conversion. You're taking 2 grams of phenol and you're converting it to moles. So the molar mass, calculated this earlier, is 1 mole of phenol has a mass of 94.12 grams. And so mole-wise, this is 0.0212 moles when you calculate this. grams cancel out. So as easy as that, the delta H is just finding the Q, or taking the Q, 64.98, and it's heat release, so it's in the end it's a negative value, kilojoules. You can put that negative at the end, or you can put it within here, the equation. So you divide those two numbers and you get your heat, molar heat of combustion, which is negative 3,058 kilojoules per mole. So that allows us, we've done A. Now we're into B. Calculate the value of the standard free energy change, which is Gibbs free energy, for the combustion of this. So now we're not given the heat of the Gibbs free energy formation values. We're given the delta H formation values, which we don't really need because here's your delta H of the reaction. So you have your delta H of your reaction already. You do need, in order to find delta G, you're going to use this equation, which means you're going to need the delta H, or the change in entropy of the reaction. So here's reaction, reaction, reaction at standard conditions. So to calculate the delta S, you just go ahead and do the S products, the sum of the products, the S formation products, which again, I like just going through it and telling myself which one's the products versus reactants. So here's my product, here's my product, here's my reactant, here's my reactant, and this is extraneous information, so I really don't need that. So the sum of my products, so my products are these two, 69.91 plus 213.6. But then I have to look at the stoichiometry with that, okay? So it looks like carbon dioxide is 6 times. So I'm going to have to multiply that 6 times. This is 3 times. So I would multiply the water, liquid water, by 3 times that value, okay? So I've got this part right here. Now I'm going to subtract it from the sum of the reactants. So I look at the reactants and I see what the entropy of the formation of those reactants are. So here I have 144, that's times it by 1, plus the change, or the heat of formation of oxygen, which has entropy. It's not 0, it's the enthalpy that's 0, and the Gibbs free energy that's 0. So 205.0, and times that by 7. So you do your math and make sure that it all looks, or your math is correct. Now, when I do my math, I end up getting 1,000, or 1491.33. And then I'm going to subtract that by 1,579. Okay, so 1,579. In subtracting those two, I get negative 87.67 joules per mole times Kelvin. So I'm going to stick with the units. Now I'm going to convert that joules per mole to kilojoules. So 1 joule, or 1 kilojoule, is 1,000. So it's basically moving it over 2 spaces. So it's negative point, or 3 spaces, sorry, 87.67. Okay? And that will give me my kilojoules per mole times Kelvin units. Now I'm ready to use the equation. So I'm going to move over here because I have a little bit more space. Delta G equals delta H minus T delta S of my reaction. So delta G is found by taking delta H, which is negative 3,058 kilojoules per mole, minus 298, which is the temperature in Kelvin, times it by negative 0.08767, and that's in kilojoules, so we're good. I'm not going to put the units in. So multiplying it all and subtracting, you get negative 3,032 kilojoules per mole for your delta G of your reaction at standard conditions. Okay, so these are all your values as you see it. Now the question is, will the reaction occur spontaneous in the forward direction? And if you look at this delta G, it's negative, so it is going to occur in a spontaneous in the forward direction. So yes, because delta G is negative.